Okay, so chapter 6, which we're starting today, covers a topic called random variables. The first section is all about background of random variables. One thing you guys already know, it's been a while though since we've talked about it, and that's the difference between discrete and continuous. So we'll review that, and then we're going to talk about mean, standard deviation. This chapter is more probability, so it's going to be pretty similar to what we just finished. When we get on to 6.2 and 6.3 then, we're going to be looking at specific variables, so on and so forth. There are some things that you're going to learn how to do on the calculator, and there is a portion of the formula sheet that applies to this section. Before we go into notes though, we're going to watch a quick video. Okay, let's just talk about in general what is a random variable and talk about a few different pieces of vocabulary. So what is a random variable? A random variable takes numeric values to describe the outcomes of some chance process. So for example, the number of people that show up to a flight, that's a random variable. We don't know how many people are going to show up. Hence why it's called a chance process. If I stand outside Mariano's and ask people as they're walking out, how much did you spend in the store today? That's a random variable. I don't know how much they will have spent. This example down here is a random variable, and it is displayed using a probability distribution. Probability distribution we already saw in chapter 5. Probability distribution shows the possible outcomes and how likely they are. I want to emphasize to you that this word distribution is really, really important, and it always has the same meaning. So you've heard this before. You might hear sample distribution. You've heard population distribution. Now you've heard probability distribution. All that differs is what is being displayed. In a population distribution, we're displaying the population. All the values, how likely they are. In a sample distribution, we're showing the sample. All the values in the sample and how likely they are. So on and so forth. Probability distribution. Again, how likely the various outcomes are. A probability distribution can be shown in a table or a graph. We talked about at the beginning of the year numeric and continuous variables. A discrete random variable is discrete versus continuous. If you remember, that means when we have a number line, we are only taking on specific values on that number line. So discrete, specific values on a number line. So there are gaps between the values. And a discrete random variable, though, can be infinite. So for example, for all of you, if I asked you, what is your shoe size? And I asked you, what is the length of your foot? Shoe size is discrete. We have certain values on a number line. 8, 8.5, 10, 10.5, 11, so on and so forth. So shoe size would be discrete. Length of your foot, though, would not be. Length of your foot could be any value on a number line. We can only measure so accurately, but length of your foot would be continuous. Do we remember those terms from a while ago? Okay, so let's take a look at this example, and that's what we will end with. Imagine selecting a U.S. high school student at random. To find the random variable x is the number of languages spoken by the randomly selected student. The table below gives the probability distribution of x based on a sample of students from the U.S. Census at school database. Okay, first question. How do we know that this variable is discrete? Why is this variable discrete? Colleen, thank you. Okay, so we're taking on certain numbers only on a number line. We can't speak 1.7 languages. So going through the question it's asking us, show that the probability distribution of x is legitimate. We've already done that before. We did that last chapter. If we add up all these probabilities, they sum to 1. B, if we made we're going to make a very quick histogram. So on the x-axis, we're going to have the number of languages. Language. And then we're going to have the associated probability on the y-axis. So I'm just going to do 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Like I said, this is not going to be great, but I just want us to get something down. So this is 1. This is 2. This is 3. This is 4. This is 5. I know it's not great, but you get the idea, hopefully. When it asks us to describe what we see, what does that mean? When we think back to histograms, what do we describe? Numeric data, CSSU. What does C stand for? Center. What does one of the S's stand for? Shape. The other one? Spread. Unusual. So we would say something like the distribution is centered around 2. It's skewed right. Goes from 1 to 5 languages. Okay, and then taking the next 2 minutes and then we'll be done. What is the probability that a randomly selected student speaks at least 3 languages? So we're taking the probability of 3, adding the probability of 4, adding the probability of 5. And that is 0.075. Okay, I do want to interpret this value. We are going to interpret it in the long run. So, in the long run, if we selected many U.S. high school students at random, about 0.075 of them, or 7.5% if you prefer, would speak at least 3 languages. Do any of you speak 3 languages? Okay. D, what is the probability that a randomly selected student speaks more than 3 languages? Is that the same answer? No. Hopefully we can tell in D, we're only adding up 4 languages and 5 languages. So that gives us 0.010. So this is really important. If our variable is discrete, like it is here, the probability of x is less than or equal to 3. Sorry, ours is greater than or equal to 3. Greater than or equal to 3 is not the same as greater than 3. can't speak at least 3 languages, and more than 3 languages are different. We're going to do E real quick and then we're done, I promise. Given that a student speaks more than 1 language, what is the probability that the student speaks 3 languages? What's the probability of speaking 3 given more than 1? Well, the more than 1 is all of those numbers. So that's 0.37. And then out of those 0.37, 0.065 speak 3 languages. And you would calculate that.